Okay, starting chapter 13 today, where it'll be sequences and series chapter, super important for calculus. And I'm listening. I just got Siri talking to me. Oh well. All right. Yes. Here we go. A sequence is a function whose domain is the set. The definition of the word function is mathematics, a mathematical relation such that each element of a given set, the domain of the function, is associated with an element of the function. The word function has okay. 9 other definitions. So, a sequence is a function whose domain is the set of positive integers or a subset of positive integers that consists of the n integers 1, 2, 3, n. So you'll just be putting in to this function only the positive integers starting with 1 and then going through n. And it's basically a sequence is just a list of numbers that will follow a pattern. And there's all kinds of sequences. 2, 4, 6, 8 is one. 1, 1/3, 1/9, 1/27 is one. 1, 1/2, 1/3, 1/4, 1/5 is another sequence. 1, 1, 2, 3, 5, 8, 13, 21. All of these are examples of sequences. So a sequence can be finite, which means that there's a specific number of terms. And how you can tell that is after this 8, there wasn't a comma, ... So this sequence has only 4 elements. This one is an infinite sequence since it's got the ... This one is a finite sequence. It only has 5 terms. And then this one is an infinite sequence since there's the ... So the infinite ones, they go on forever and ever. So before we do an example, hopefully you can look at these and see, oh yeah, I can see the pattern of this guy. 2, 4, 6, 8. It's just the even numbers. This one, hopefully you see the pattern on this. This is a 1/1 and a 1/3 and a 1/9. To get to the next term, you would just multiply by 1/3. This one is a sequence where the denominator is 1 here. So it's 1/1, 1/2, 1/3. So it's just the sequence where the denominator, well, the numerator is all 1s, and then the denominator is increasing by 1. So this is just 1/n. And then this sequence is a famous one. You probably learned it in middle school. It is the Fibonacci sequence, where you get 2 from adding the 2 terms right before it. You get 3 by adding the 2 terms right before it. 1 + 2. 2 + 3 gives you 5. 3 + 5 gives you 8. And so that's how that one is defined, where it starts with 1 and a 1, and then you get the next term by adding the 2 right before it. All right, so let's do an example. We want to find the first 5 terms of the infinite sequence defined by, so here they give you an explicit rule. They tell you exactly how to find each of the terms. You start by just plugging a 1 into n to get the first term. That would be plugging in a 1 into here. It would be 2 times 1 + 3 gives you 5. Plugging in a 2 into n will give you 4 + 3, which is 7. Plugging in a 3, 6 + 3 gives you 9. Plugging in a 4 gives you 8 + 3 is 11. And then plugging in a 5 gives you a 10 + ... which is 13. And so your infinite sequence is, the first 5 terms would be 5, 7, 9, 11, 13, and then the ... to represent that it is an infinite sequence. It's going on forever and ever, and it's not ending. These are called the terms: first term, second term, third term, fourth term, fifth term. We're going to be using some math notation for that you're going to hate, but that's all that it's referring to. This is the math notation I was talking about. We can use a sub n to denote a specific term, such as a1, a2, or a10. This means the first term. A2 means the second term. A10 means the 10th term. And then the general term a sub n is the nth term. And the formula used is called the rule of the sequence. So find the 19th term of the sequence given by the rule b sub n is equal to 3 to the power of n minus 1. Well, if we're just finding the 19th term, you're plugging in 19 into n, so 3 to the 19th minus 1, which of course you'd have to use your calculator for, and it's this very large number. So a rule like example 2, where they just give it like this, is called an explicit formula. You're able to just plug in whatever your nth term number is and plug that number um, into n and find any value. So we're going to work backwards now. Now I give you the sequence 10, 20, 30, 40, and we're going to find the explicit formula for this. So I notice that it starts with 10, and I'm adding 10, and I'm adding 10, and I'm adding 10. And so doesn't it make sense that it's like a 10 times 1, 10 times 2, 10 times 3, 10 times 4? So the pattern is just 10 times n. This pattern, a little more complicated. Take the numerators and denominators separately. That's what I always go for first. Look and see, can you find a different pattern for the numerator than from the denominator? And this one is definitely true, that all of the numerators are 2's. So my pattern will be 2 over, and then this is 3 times 3 will give me 9. Times 3 will give me 27. Times 3 gives me 81. So these are actually powers of 3. 3 to the power of 1, 3 squared, 3 cubed, 3 to the 4th. And so the pattern is 2 over 3 to the power of n. If these are difficult for you, don't stress. Next, your pre-calc book is famous for making you just kind of work it out organically at first and then giving you formulas. And so you will be given formulas on exactly how to find this to generate the patterns of these sequences tomorrow and the next day. So don't stress if you go to do the homework and these are kind of hard to find. Don't stress too hard. You'll actually have a specific way to find them tomorrow. Now it's just, can you just generate what you think the pattern is? Another way to give a rule for a sequence is using a recursive formula. It gives an initial term, it gives you the first term, and then it defines the nth term using a preceding term, using the term before it. The Fibonacci sequence is the perfect example of a recursive formula. There you go. Classic example is the Fibonacci sequence. It will always give you, well, for Fibonacci, they'll give you term 1 and term 2. They tell you the first term is 1, the second term is 1, and then they say that the nth term is found by adding the 2 terms right before it. Now, this looks really scary, but don't freak out. Right? This is just very mathy notation for just saying my first term is 1, my second term is 1, my nth term is equal to the term right before it plus the term right before that. That's what the n minus 1 and the n minus 2 is. And then it's for n is greater than 2 because I gave you first term and second term. I know that looks scary, but it's not too bad when you start working it out. All right, let's find the next 4 terms of the sequence given by this recursive formula, where the first term is 3, and then the nth term is found by taking 2 times the term right before it, minus 1, and this is for n greater than 1, because they only give you the first term. Okay. I just work it out. All right, so let's switch to a pen real quick, and let me show you how we work this out. All right. So to find the second term, it'll be 2 times, well, actually, all right, 2 times, all right, the first term, because that's the n minus 1. If n is 2, then n minus 1 is 1, and then minus 1. So that gives you a 2 times 3, and then minus 1. 6 minus 1 gives you 5. All right, so now I have the second term. To get the third term, it is 2 times 3a sub 3 minus 1. So 2 times a2 and then minus 1. But we just found a2. We found that it was 5. And so that'll give you 9. How many do we want the next 4? Okay, so the fourth term will be 2 times a3 minus 1, which is 2 times the 9 we just found. That's 18 minus 1, which will be 17. And then the fifth term, so 5, is 2 times the fourth term minus 1, which is 2 times 17, and then minus 1, which will be 33. All right, so for some reason I didn't show that work on the PowerPoint. I went straight to, here you go, here's the numbers, but that's how we're gonna get them. I'm gonna erase all of this, and back. And so that's where we get 5, 9, 17, and 33. Sequence can be defined by either formula, recursive or explicit. And so sometimes we may give you an explicit formula and ask you to define it recursively. Other times we may give you a recursive formula and ask you to find it the explicit formula. Not all sequences can be defined explicitly, like the Fibonacci sequence can only be defined recursively, but when they can be, then we do this. All right, so we're going to find the explicit formula for the sequence defined recursively by the first term is 7, and then the nth term is the term right before it, plus 3 for n is greater than 1. All right, so let's write a few terms. Your next term, your second term would be 7 plus 3, so 10. And then the next term would be 10 plus 3, 13. The next term would be 13 plus 3, 16. 16 plus 3 gives you 19. All right. And this one, okay, so I just straight up give you the formula. You will learn, you learned it last year in Algebra 2 Trig also. You will learn a formula for generating this all the time, right? But you need, when n is 1, you need it to be 7. And when n is 2, you need it to be 10. Let's do that. Let me show you the notation on this. And then things will make more sense tomorrow when I actually give you a formula. So this is A1, and A2, and A3, and A4. And A5. And each time you're adding 3, plus 3, plus 3, plus 3. So you can't just do 7 plus 3, right? To get your n, when n is 1, you've got 7. And so this guy, I think I'm going to have to, let's see. Yeah, this nth term will be 4 plus 3n. And you may not have seen that right away, but hopefully you see it now that if you plug in a 1 into n, you would get 4 plus 3, which will give you the 7. When you plug a 2 into n, you'll get 4 plus 6, which will give you 10. When you plug a 3 into n, 4 plus 9 gives you the 13. And so even if that didn't seem super obvious to you at first, it will tomorrow. Tomorrow I give you the formula for finding the explicit formulas on these guys. So don't stress too much if tonight's homework, when you're given something and you're having a hard time, don't stress too much. Look up the answer and go, oh, okay, yeah, that makes sense. And then tomorrow I'm going to give you a way to totally find this super easy. We can also, if given enough terms, discover a recursive formula. So Mrs. Fox decided to ease into saving her tutoring money. The first week she set aside $1, and then the second week $2, and the third week $4, the fourth week $7, and so on. So it generated this sequence of 1, 2, 4, 7, 11, 16, 22. Find a recursive formula for the sequence. So here's my thoughts. On the first one, from 1, we added 1. But for 2 to get to 4, I added 2. Then from 4 to 7, I added 3, and then I added 4, and then I added 5, and then I added 6. So your first term is 1, and then I'm adding, your nth term would be the term right before it, but then plus, you're actually adding n minus 1. Let's see. You got plus 1. Plus 2. So for the second term, you're adding 1. For the third term, you're adding 2. For the fourth term, you added 3. For the fifth term, you added 4. So does that make sense that for the second term, you added 1. For the third term, you added 2. For the fourth term, you added 3. So that's where the n minus 1 is coming from. Fourth term was equal to the third term plus 3. Yeah, and these two guys were matching. And you always have to include this n minus 1 also. Oops. Okay, that's it. Again, don't freak out too bad. Again, your book does this whole like, can you get a general sense and a gut feeling on all of this? But tomorrow we will totally give you formulas that you can just generate any of the sequences. You may remember them from last year. Very possible. Discard those. All right. I hope you all are having a fantabulous day. And come see me in office hours if you have any questions. All right. Okay. Have a good one. Bye.